Hello, my name is Ali Gambari and I'm a PhD student at the University of Texas at Dallas, working under the supervision of Professor Andrea Marquez. We are presenting our work toward speeding up mutation analysis by memoizing expensive methods. Mutation analysis is a program analysis technique intended to measure the quality of a test suite by counting the number of injected artificial bugs that it can detect. The basic idea is that the more artificial bugs a test suite can detect, the more adequate it is and the more likely it will detect real bugs. Let's look into an example. This is a program that, given three integers, checks if the three numbers could form a triangle, and if yes, what kind of triangle they form. Assume that the program is tested by using a set of test cases. I'm using a symbol looking like a traffic light to represent test cases. Each traffic light corresponds to a test case. Green light means that the test cases are green, that is, they are passing. And red light means that they are failing. As you can see from this example, the test cases of this test suite cover various portions of the source code, and they are all passing. Now we can use mutation analysis to measure how adequate this test suite is. That is, had we had a real bug in the code, would the test suite be able to catch the bug? Mutation analysis starts by generating a pool of program variants called mutants. Mutants are generated by applying simple transformations to the program text, for example, flipping a comparison operator, an arithmetic operator, etc. As we can see in this hypothetical example, transforming AND operator to OR operator makes two of the test cases fail. When a mutant results in a different system state propagated to the test code and make any of the test cases fail, we call the mutant is killed. So the mutant corresponding to this transformation is marked as killed. We might have a different transformation that does not result in any test failure. If such a mutant is not equivalent to the original program, we call it a surviving mutant. So for this hypothetical example, we generated two mutants out of which one was killed. We can approximate mutation score by dividing the number of killed mutants by the total number of mutants. The more mutation score a test suite achieves, the higher quality it is. In other words, the higher the mutation score, the better the test cases are in catching artificial errors and more likely to catch real errors, that is, the better test suite. Mutation analysis has many applications beyond its original application in assessing test suite adequacy. These applications include fault localization, automatic program repair, test input generation, security analysis, etc. For each mutant that we generate, we have to execute the test suite to see if we observe any failure. Since depending on the size of the program, we usually generate a large number of mutants, executing the test suite against each and every one of the mutants creates a performance bottleneck. Researchers have proposed various approaches to speed up mutation testing process: selecting and reordering test cases, running test cases concurrently, eliminating equivalent mutants, predicting mutation outcome, reusing system state between execution of mutants, etc. In this work, we propose Memo, which stands for Memoized Mutation Analysis. We take a novel approach to speeding up mutation analysis by transforming production code so that the expensive methods use memoized results when pre-recorded inputs occur over and over again during mutation testing. Memo can be seen as having a linear architecture like this. We have a pre-processing phase in which we start with a static call graph analysis. Once we constructed the call graph or make call relation over the set of all methods, we use it to gather various information about the target program. This includes identifying likely deterministic methods. We don't want to memoize methods that we suspect that will behave non-deterministically, for example, those that make calls to time-related functions or use random generators. We can identify such methods by using simple pre-processing and a data log program as shown in this slide. Another useful information that we obtain based on the call graph is the side effect information of the methods. That is, each method is accessing which fields directly or indirectly. This information becomes useful when we clone object graphs without cloning portions of the graph that are not touched by the method to be memoized. Another important ingredient of memoized mutation testing is the dependency relation, which is essentially transitive closure of the call graph. We use dependency relation to figure out which methods might be implicated by certain mutation. If a method is implicated by some mutation, we should not memoize it, as by doing so, we will cover up the mutation. We don't want to memoize each and every method in the program. We want to memoize only the expensive methods. In order to identify expensive methods, we measure the execution time of all the likely deterministic methods and select top L methods that take at least 10 milliseconds to run as candidates for memoization. We then instrument the program to record input-output pairs for all candidate expensive methods. In this way, we construct a memo table for each method. These memo tables are stored in a database. During mutation testing, we have to load memo tables database each time we create a process for testing mutants. Since memo tables database can easily grow, this imposes a large amount of overhead on mutation testing. Additionally, not all the recorded methods are actually memoizable, or some of them have a little cache worthiness. To reduce the size of the memo tables databases and getting rid of the methods with less cache worthiness, we tentatively memoize each of the recorded methods and run the covering test cases against the methods to filter out the methods that cause failure when memoized or result in less than 100% cache hits. Once we prune the memo tables database, we start actual mutation testing process. Once the mutants are generated, we instrument each mutant in such a way that the likely deterministic expensive methods reuse the memoized data instead of re-executing the body of the methods each time they are invoked. We have implemented a prototype of Memo and have applied on 12 real-world Java projects. Memo achieves on average 18% speedup. The current implementation of Memo inflicts overhead in the pre-processing phase that outweighs the speedup that we gain during mutation testing. We are currently working on reducing this overhead by constructing faster analyzers. Thank you.
Hi, everybody. Hello, and welcome to this second paper in the session of mutation testing. Unfortunately, the author is the second no-show at all ICSE, so we don't have anyone to help us answering the questions. So please leave your questions in the chat. He might come back at a later stage. So sorry, Raul, for all your good questions there. So you can go and grab a little tea, coffee, have a break until the next paper and stretch, because I'm sure you have sitten like me and been a glue. And the next paper is really exciting. It's about what it would take to use mutation testing in industry. So I will not babble anymore, and thank you again, and have a look in the paper and see you soon. Okay, love.